Exponential differentiation. In the last lesson of this calculus course, we will talk about exponential differentiation and exponential integration. So it's just a couple ways, or a couple new derivatives and integrals to look at to close out this course. The first derivative with respect to x of e to the x power simply gives you e to the x power. So there's your first derivative. This is very specific. This is e to the x power. However, we could also have e to some power u, where u is a function of x. And if you have this, then when you take the derivative with respect to x, you will get e to the u power times u prime, where u prime is the derivative of u. Or you could write it e to the u du, where du is the derivative of u. And it is important to note that u prime, or du, however you write it, is not in the exponent. So let's take a look at a couple of examples here. Find the derivative. In this first example on the left, we have y equals e to the cube root x power. The first thing I want to do is rewrite this cube root x as x to the 1/3, like this. The next thing that needs to happen is recognizing that you have e to some power. And when you take the derivative of this, if it's in a certain form like this, y equals e to the x, then the derivative will just be e to the x. Well, that is not the form we have. What we have over here instead is y equals e to the u power. I'm going to replace these x's with u. So when you take the derivative, that means you have to multiply this e to the u power in the derivative by the derivative of u. So x to the 1/3 power is the u. So when you find the derivative of this, y prime equals e to the x to the 1/3 power, and we still have to do this portion here, multiply that e to the u by the derivative of u. And in order to figure that out, you just use the power rule. So this is 1/3 x to the negative 2/3 power. And then if we rewrite this, moving the x to the 2/3 power to the denominator, you'll get y prime equals 1/3 x to the 2/3 power times e to the x to the 1/3 power. So this is your derivative for the first example over here on the left. On the right, there's another example here. Y equals e to the 2x power over e to the 2x power plus 1. Now with this, there will definitely be a quotient rule used. So the quotient rule states that the derivative is the denominator times the derivative of the numerator minus the numerator, e to the 2x power, times the derivative of the denominator, e to the 2x power plus 1, all over the denominator squared. There we go. From here, I will take the derivative of these terms, and I'm going to have to use the same idea that I did over here in red. So I will take the derivative of e to the u power and get e to the u power, but then I have to take the derivative of the exponent and multiply that out back. And when you do that, you'll get something like this. So if you look here, e to the 2x power, when you take the derivative of this, you just get to copy this down as part of the derivative, e to the 2x power. Then you have to multiply to it the derivative of the exponent. The derivative of 2x is 2. And the same thing happens over here with this derivative. The derivative of 1 is 0, so we don't need to write that here. But the same thing, e to the 2x power becomes e to the 2x power times 2. So the last thing that needs to happen here is simplify the numerator and then simplify the entire fraction, if we can. So simplifying the numerator, I need to take this term here and really call it 2 times e to the 2x power and distribute it here. I need to multiply this portion out and you will get the following. When you multiply like bases, so here we have a base e and a base e, we can add these exponents to get 4x exponent. So it would be 2e to the 4x power. And we have 2e to the 2x power times 1, so it's just 2e to the 2x power. And similarly over here, since we have like bases, we can add these exponents together. 2x plus 2x is 4x. So minus 2e to the 4x power. Then this cancellation happens in the numerator, and we're left with y equals 2e to the 2x all over e to the 2x plus 1 squared. So there's your derivative for the second example. On this page, we will still be finding some derivatives, but we have different instructions. So in this first example here, it's asking to find the equation of the tangent line at the point 1 comma e. So if you look at this derivative, or at this function, we will still be needing to take the derivative because that is how you find the equation of a tangent line. So when you look at this, we have y equals x squared times e to the x power. So it looks like a product rule will be happening here, minus 2x times e to the x power. Another product rule will be happening here, plus 2e to the x power. This won't have a product rule. We'll just need to use exponential differentiation. But upon further inspection of this function, if we notice that every term has an e to the x power, we can make life a lot easier here. E to the x power times x squared minus 2x plus 2. If you common factor out the e to the x power, that means now we will only need to do one product rule. So that being the case, I'm going to find the derivative of this. It'll be the first times the derivative of the second plus the second times the derivative of the first. Here's what that looks like. From here, to find the slope of a tangent line, we need to come back and look at the point that was given to us. Find the equation of the tangent line at 1 comma e. Well, this x-coordinate is very important to finding the slope of the tangent line. We need the slope of the tangent line before we can find the equation. So this 1 will get substituted in for each x in our derivative. And when you do that, it looks something like this. So x was replaced with 1 everywhere. And what this does is after you simplify all of this, that will be the slope of the tangent line. So when you go through and see that 2 times 1 minus 2 is 0, that means this entire first term is 0. And 1 minus 2 plus 2 is 1. So this entire term here is 1 times e to the first power, it's just e. You get that the derivative is e. And that ends up being the slope of the tangent line when x equals 1. So this is important here. E is the slope of the tangent line when m equals 1. So what does that mean? That means we will have an equation of a tangent line, y minus y naught equals m tan times x minus x naught. And it's been a while since you've seen this, but the y and the x will stay y and x. The slope of the tangent line we just figured out is e, and the x naught, y naught come from way back over here, what we started with. The 1 is your x naught and the e is your y naught. So we can substitute these values in here. So y minus e equals e times the quantity x minus 1. So there is the equation of the tangent line at the point 1 comma e of this function. In this other example over here, this one will go a little quicker, I believe. We need to just find the slope of the tangent line at 0, 0. And with that, we will need to use the product rule again. But this time, there is some trigonometry thrown in with it, just to bring that back to memory. So the product rule again is the first function times the derivative of the second function plus the second function times the derivative of the first function. Looks something like this. So again here, with finding this derivative, the first e to the 2x times the derivative of the second. The derivative of tangent is secant squared, 2x, times 2, there's a chain rule there. The 2x is on the inside, the chain rule is on the outside. Similarly, when you find the second part of the product rule, it's the second function, so tangent 2x times the derivative of the first function, e to the 2x. Well, since this is not just x, this is some function in terms of x, we need to multiply that by the derivative of the exponent, which is 2. So now the only thing left to do is to substitute 0, this x coordinate, in for x everywhere here to get a tangent line slope. So all of the x's have been replaced with 0. And the nice thing about this second term is that the tangent of 2 times 0 is really tangent of 0. And tangent of 0 is 0. So this whole second term turns into 0. While this first term is y prime still equals e to the 0 power in this first part is 1. And secant of 0 is also 1. So e to the 0 power is 1. Secant to the 0 power is 1 times 2 plus 0. So this whole slope, this big complicated looking slope formula that we'll get for the slope of any tangent line for this function at 0, 0 simply turns out to be 2. That is our m tangent when x equals 0. Implicit differentiation. In this example, we will implicitly differentiate this function, 1 plus natural log xy equals e to the x minus y power. So the first step here is to find the derivative of each side. So on the left side, the derivative of 1 will be 0, and the derivative of the natural log of xy will just be 1 over the argument, that's what's on the inside, times the derivative with respect to x of x times y. And this will create a product rule situation for us a little bit later. On the right-hand side, remember, e to any power, when you're trying to find the derivative of that, will just be e to that power, that same power. It's almost like cheating. You just get to copy that down, times the derivative of the exponent, x minus y. So on the left side of this equation, we still have 1 over xy times, here's where the product rule is going to kick in. When you use the product rule, it's first times the derivative of the second. Now we're going to treat y just like x. We're going to take the derivative of this using the power rule, and that gives us 1. But since we took the derivative of the y variable, we need to immediately attach a y prime. So that is the first part of the product rule here. To that we're going to add the second function, which is y, times the first derivative of the first function. Derivative of x is 1. This will be equal to e to the x minus y power times the derivative of x is 1 minus the derivative of y is also 1, but since we're taking the derivative of y, we need to tack on that y prime right afterward. From here, the next step, I will clean this up a little bit, like this. And the last thing that needs to happen is now solving for y prime. And the first thing I want to do in order to solve for y prime is first get rid of this fraction. So that means I'm going to be multiplying both sides times xy. And that gets rid of this fraction, which will make solving for y prime a lot easier. So the last thing I need to do is distribute this here and this here, get all of the y primes on one side of the equation, anything without a y prime on the other side, common factor out a y prime if I need to, divide, and you'll get something that looks like this. So there is, in fact, a lot of algebra happening between this step and this step. Go through and see if you can figure all that out. This is the answer for the implicit differentiation of this function we started with.